So it is Wednesday, right? It's the second day of class, and this is Biology 105. Today we'll be covering Chapter 2 on chemistry of the cell. Last time we did Chapter 1, and you've also, all of you now have been in lab. And so if you look on your syllabus, you'll see that what you need to do for the first exam is what? Look at your syllabus. What's on the first exam? It tells you that it's not until after Memorial Day. It's still a ways away. But it's going to be chapters 1 and 2 and the material you covered in Lab 1. You've already been to Lab 1. The body terms, the directional terms, the planes, all that content. That's what's going to be on exam number 1. I'll cover most of Chapter 2 today. I probably won't cover all of it, but I'll get a large chunk of it done. And that'll leave a little bit of Chapter 2 for next Monday. And then after that, we'll be learning new material, but you'll have lots of time now to master and really focus in on the things on first exam. I also want to make sure that you vocabulary, right, 1 through 20 on the first exam. So let's go ahead and go there right now to the vocab. And last time, I think we only did the first 4 slides. Is that right? I should have done the first 5 slides. So let me go ahead right now and just go on to 5 and go through 10 with you. That way we'll be on a good sequence of doing about 5 slides every day. Remember, I told you that what you'll want to do is make note cards. And for the note cards, what you'll want to do is simply put the meaning on one side of the card, and on the other side, put its meaning. You don't have to worry about the example. Okay? So if you put on one side of the card AN, and on the other side without or lacking, and anesthesia is an absence of pain, esthesia is pain. We'll get to that. Esthesia, we'll get to that word later. That means pain. So lacking pain. So andro, male. Androgens are a bunch of hormones that are produced largely in males. Angio, pertaining to the vessels or the blood vessels. Angiology would be the study of blood vessels. Angiogenesis we'll talk about later. That's the formation or the production of blood vessels. And then aqua, this one's pretty easy, water. Anti, before. Antibrachial, antecubital, right? Or antepartum, before birth. Maybe you're more familiar with that one. How about anti, meaning against? An anticoagulant is something that's going to fight against the coagulation or the clotting of the blood. Apo, separated from, and APS or APT both mean to fit or to fasten. Now, the example here you may not know, but maybe some of you know about a synapse. A synapse is where 2 neurons come into close proximity, where they fit or come together. So the APS part tells us they fit together, and syn, S-Y-N, we'll learn later, means to come together, right? Where they fit together, synapse. Question?
Can you give an example of the an APT word?
That one, synapse.
No, one that has APT.
Oh, APT? Not off the top of my head, but thank you. No, I can't think of one with APT in it, but I'm sure there are many, and I'll come up with one at some point. AR, another negating term. So A or an or AR all mean without. So arrhythmia, right? Lacking rhythm. Arche, the beginning of or the origination of something. Menarche, the beginning of the menstrual cycle, the first menstrual cycle. Arthro, joint. Arthropods are critters with large feet and joint structures like lobsters, or arthritis, an inflammation of the joint spaces. And then atrio, this is a typo. It should be A-T-R-I, not artrio, but atrio, A-T. Drop out that first R. So get rid of that first R. But atrio refers to an entryway. So your church or home, you may refer to the entryway as the atrium, right? And the atria are the openings into the heart. So blood first comes into the heart, into the atria. Okay? So get rid of that R. Airy. If it ends in airy, associated with urinary, associated with urine. Terms that end in ASE are almost always enzymes. We'll be talking about enzymes today. Enzymes are biological catalysts. They are proteins. And some examples would be polymerase and kinase. Again, you're not responsible for those examples, but you'll see the ace on the end of them. If a term ends in acis, it's a condition or state of homeostasis, a state of keeping things what? Homeo, same or similar, right? And then finally, asthen is a weakness, so myasthenia would be what? A muscle weakness. Very good. Athero, fat. You've heard of atherosclerosis. Sclero means hard. Osis, a condition of. So a condition of hardening of the fat. So there's fat that's building up in the arteries causing this hardening. Audio, hearing. We got that one, auditory. The outside of your ear, the flappy portion of your ear is called the auricle. So ari meaning ear. And auto, self. Automobile, literally to propel oneself. Okay. And then finally for today, halfway through the vocab for the first exam, baro. Barometer, an instrument that measures pressure. Bariatric surgery, surgery that helps to reduce weight. Benny, good or well. If you are told that you have a benign tumor, that's really good news, right? Because it's a tumor that's not growing necessarily very fast. Likely it's not going to kill you. And benediction, if you give a benediction, you're giving a good word. Twice or double, bi. Okay, so bicuspid, teeth with 2 points on them. Bicycle, right? Two wheels. And then finally, bio. Here we are in a biology class. We're learning about the study of life. Bio meaning life. Ology, the study of a biopsy. What are you doing? You're looking at living tissue, right? So opsy meaning to view or to look at, and bi, you're looking at something that is living. Okay, biopsy. That's halfway through. And where are we going again? We're going down to, I believe it's cusp. So go ahead and make up those slides. We'll finish up those vocabs 5 at a time. 5 more on Monday, 5 more the following Wednesday, and that'll still give you a week to let all those sink in and be really, really successful. I also gave you a strong hint as to how I will quiz you on this. Back around slide 4, I told you that on the exam, as an example, I would say to you, what does ambialgia mean? You would have already known with confidence that ambi means both and that algia means pain. So you would tell me for 2 points, pain on both sides. Okay? So that's the way you're going to be doing this. When you make up your note cards, play a game with yourself. Put them out on the table and try to fit words together. Just kind of imagine the same thing that I do. I sit there and I take the cards, I literally do, and I try to find new and creative ways to quiz you on them. And most of the time, the words I ask you are actually in the dictionary. Occasionally, the word I ask you may not even be a real thing, but you would be able to figure out what it means based upon the 2 parts.
I know there are several words or endings that mean the same thing.
Yes.
Kind of a trick is remembering which one, like for pertaining to which one's
Ac and al. Ac and al. I don't know, they're cousins. I don't know. I mean, there are some repeats. You might want to put them on the same card. It's up to you. I mean, you could put A and AN and AR all on the same card. They all mean without or lacking. You could put ac and al on the same card if you wanted to. They both mean pertaining to. Okay? But I don't really have any tricks for this except just repetition. So again, my recommendation is always just to get some flashcards, flash through those cards 5 minutes every day. Just 5 minutes every day. That's all. And by the time 2 weeks comes, you'll have these so well known that you'll just go right through that little section of the exam with no concern. And you won't be spending any valuable time the night or two before the exam cramming for the vocab. This is not meant to be, this is not meant to be punishment. This is meant to be a tool to help you be more successful so that as you're reading words and you're coming across words for the first time, you can hopefully unpack them and figure out the meaning. Okay? Making sense on the vocab? And we'll just keep running through this, 101 slides. And by the end of the semester, we'll have gone through all of them, and they are not cumulative. However, I will always be coming back to them and saying, you should know what this word means during lectures. I will not quiz you directly on old ones on future exams. So exam 1 will only have 1 through 20. Exam 2 will have 21 through 40, I think it is. And that will be sequentially broken up through the semester. But these are terms that you will be constantly reminded of as we move through. I also think the vocabulary gets easier. And the reason it gets easier is as we go through the course, this is an alphabetical listing, but as we go through the course, more of these words you will have already used in this course. And you'll have more connections to make as you learn some of the new ones. Okay, so that's the vocab. So let's now go back and get into Chapter 2. Before I continue, though, are there any questions over anything we discussed in Chapter 1? Yes, ma'am. That's what you've been told till Monday. So the bookstore won't have Amerman, the lab manual, until Monday. What I will do then is I will post the units 2 and 4, which are the 2 units you would have done in Lab 2. And I'll go back tonight and I'll post those, PDF them to Blackboard. They'll be under Lab 2. And if you don't have your Amerman book, you'll be able to print out those 2 units, 2 and 4. The pre-lab instructions are in your supplement. So you'll have your supplement already, right? The yellow covered or the goldenrod colored cover. There you'll see the instructions for Lab 2. It'll refer you back to pages within Units 2 and 4 of Amerman, and you'll be able to print that out and do those activities. So there's no problem getting your pre-labs done. By then we should be all set. How many folks do not have their Amerman book? Okay, there's about half a dozen of you. So very good. So hopefully that's taken care of. Have you let them know that you want one? It's one thing to stop by and see they're not on the shelf, and they don't know to order one. So if you have not said to them, I don't have it and I need it, they may not have ordered you one. They may even have you prepay it, right? So, but at least let them know that you need one so that they will make sure they have ordered enough. Sorry about that. Okay, anything else on Chapter 1? Anything, look back through your slides. Just take a moment. Anything back in Chapter 1 that needs to be clarified? It was that hierarchy, wasn't it, from atom to atom? Right? ATOM to ADAM. Atoms. Let's go through that list together. So from the simplest layer. Atoms. Give me an example of an atom. Carbon. Good. And then we get to what level? Molecules. Give me an example. Carbon dioxide. Then the next level. Macromolecules. 4 types. Lipids. Proteins. Carbs. Nucleic acids. From the macromolecules, we now are going to make organelles. Things like cell membrane, Golgi, rough endoplasmic reticulum. We'll be talking about these, the lysosome. Those organelles are now the building blocks for cells. There's over 250 different kinds of cells in your body, and you have over 75 trillion cells making up you. Those cells are the fundamental living thing. Now, what do those cells do? They combine to make tissues. 4 types of tissues. Connective, muscle, epithelial, nervous. Okay? And we're going to spend a whole chapter unpacking that and understanding that better. But 4 basic types of tissues in no particular order: connective, muscle, nervous, and epithelial. Okay. Then those tissues are the foundational building blocks for organs. Things like heart, liver, brain, kidney. And those organs now combine in unique ways to create organ systems, of which there are how many in your body? 11. And in the room? 12. And then all those organ systems are making up you as the organism. That's a really important hierarchy, just to have that understood. And our course is kind of following along that hierarchy, because here we are today talking about chemistry. So we're going to be talking about the atoms, and we're going to be talking about the molecules and the macromolecules. And that's what Chapter 2 is all about, okay, is those first 3 layers of atoms, molecules, and macromolecules. Then Chapter 3 will be into the cells and the tissues, okay? So that's where we're heading. And then eventually, not too long from now, we'll finally get to the first systems and to the first organs. Okay, so Chapter 2. Anything else about Chapter 1? Anything all about Chapter 1? Feeling comfortable? Okay, so let's move on. Chapter 2. Again, don't forget to get all your PowerPoints done. Start making your note cards. And I'll have this lecture posted by this evening. Okay, so I download this. It takes a few minutes for that to happen, and then it takes a few more minutes for it to upload to YouTube. After it uploads to YouTube, then I have to get the code and go on to Blackboard and post that link. So there's a few steps involved. But now that we've got this technology working in this classroom, I'm confident that I'll get used to it and get it out to you very, very quickly. Now, here we are in this continuum. I should have gone to this slide a moment ago. So what we're going to be doing today is the atom and the molecule level. So this is where we're focusing today, and also a little bit on the macromolecules. The next chapter will deal with the organelles, the cells, and the tissues. Now, we already know that cells are made up of organelles. So what are organelles made up of? Going backwards. Yeah, the macromolecules, right? And going backwards again, the macromolecules are made up of the molecules which are composed of the atoms. Like, we just went backwards. So we better understand what atoms are. Right? That's really where we need to start. What are atoms? We're not going to become chemists here, but I do want to introduce the basic ideas of what atoms are, and we'll see why that's so important as we understand our own physiology and how our bodies work. So we have to have a basic understanding of chemistry. Now, this is sort of like the first day of a chemistry class, or maybe the first day of a physical science class. Matter is anything that occupies space and has mass. That's one of those definitions I know was drilled into your head somewhere in late middle school, right? That matter is anything that occupies space and has mass. So what's mass? Mass is the amount of stuff, right? The amount of matter in an object. It kind of almost seems like circular language in a way. Now, what other word do we use rather than mass in everyday language? I don't say, what's the mass of that object? I say, what is the weight of that object? Are they the same? In our everyday language, they are, aren't they? But to a chemist, to a physicist, to a biologist who's really thinking about this, they're not the same. What's the difference? Mass is a constant. It's how much stuff there is. Whereas weight changes based upon what? Gravity. If I step on my bathroom scale, I see a number. I don't like it, but I see a number. If I take my scale and my little old body up to Mount Kilimanjaro and I step on my scale, am I going to weigh more or less or the same? I'm going to weigh less. Why? There's less gravitational pull, pulling my body down onto the mechanism of the scale. If I take my scale and my body up to the moon and I step on it, how much am I going to weigh? Essentially zero. But if I bring a mirror to the moon with me and I look in the mirror, what am I going to see? Me. So my mass hasn't changed, right? I'm still the same number of molecules making this body up, but my weight changed because the gravitational field changed, okay? So weight and mass are not exactly the same. I just want to go through some of these basic, ideas because we'll be talking about mass. What is your mass? What is your weight? And I want to make sure you understand the difference in those two. So when we think about the atom, okay, over here in the room we have a periodic table. You're not going to become a master of that. I'll point out a couple of things on it and we'll understand what that's all about. But what the periodic table does is it arranges all of the elements on the Earth into a very reasonable arrangement. And what we see is that each element, things like gold, oxygen, carbon, if I have a big old chunk of carbon in my hands, or maybe easier to imagine a big old chunk of gold in my hand, if it's pure gold, what is that gold made up of? If I have a big old chunk of gold, that gold is fundamentally made up of millions and millions, and too many numbers to think about, atoms of gold. Right? It's pure gold. It's made up of atoms. Right? Atoms of gold. And if I had a big old chunk of carbon, and it was pure carbon, it would be made up exclusively of carbon atoms. Right? So what we see is that each thing on the planet is made up of fundamentally these little atoms. And there are about 112 or so elements that are on the Earth's surface, that are naturally there. Now, physicists and chemists are always trying to push it a little further and make a few more, and those are usually very unstable, radioactive, not something that's presently found on the Earth. Of those 100 elements or so that are found on the Earth, only about 20 of them are required for life. You know most of them, maybe you don't understand them, but look on your vitamin bottle, right? And you're going to see on there some chromium and some molybdenum and some other magnesium, and you're thinking, why am I putting this into my body? Well, it's one of the elements that is necessary to sustain life, and we need to have those. Of all of your body, about 96% of your entire body is made up of just 4 elements: carbon, oxygen, hydrogen, and nitrogen. Those are the 4 biggies. They make up 96% of who you are. It's been said that if you were to sell your body's elements and atoms on the free market, it's worth about $6. You're not worth a whole lot. Carbon's not exactly a rare element, right? So those are all very common. You got a little bit of gold in you, you got a little bit of rare stuff, but for the most part, you're worth about $6 in a heap. Okay, it's kind of a grotesque way of thinking about it, but it is kind of cool though when you think about the complexity of our body coming down really to being a collection of atoms in very special arrangements. So atoms then are the basic unit of matter. All things are made up of atoms, and these atoms are going to control the chemical reactions that occur within our body. And that's what we need to understand, that we have all this metabolism going on. Metabolism is a fancy way of saying all of the chemical reactions happening in your body. You might take a course in biochemistry, right? Learning about all of the reactions occurring in your body. So we better understand atoms. Now I said a moment ago we were going to start at the level of atoms. And that's true. But atoms themselves are made up of smaller things, and I want to introduce those. Now, if you were taking a course in physics or quantum mechanics or something, you would learn that even these things are made up of smaller and smaller things, and we don't have it all figured out yet. But we'll start here saying that an atom is a physical structure that consists of a nucleus. Now, the nucleus is just like what you think of for the cell. It's the center, right? It's the center of the atom. It's usually the center of a biological cell. And around that nucleus, now we're talking about the atomic nucleus, around the nucleus there are going to be electrons floating around. So this is sort of a cartoon model of an atom on the bottom. That very center little red guy, that represents the actual nucleus. Okay? And the blue cloud that's all around it represents where the electrons would be found associated with that atom. Another way of describing it, as I've been told, is if this was my alma mater, Florida Field, or the big house, right, some big football stadium, and you were to dangle something of the magnitude of I've heard pea or grape or apple over the 50-yard line, dangling from halfway up. The stadium itself and all the seats would represent where all the electrons could be, and that apple would represent the nucleus. Right? So we're talking about a very, very small nucleus surrounded by a relatively huge field called a cloud where the electrons are hanging out. So let's go a little bit further and figure out why we care. So the atomic structure, we have the nucleus, that very center, that little core. In the nucleus, one finds protons. Protons are positively charged, P, positively charged. That's why they have a little P plus as their abbreviation. And the number of protons actually defines what element we're dealing with. So, as we look at the periodic table, as we will in a moment, or if you can even see it over here in the room, hydrogen, for example, is the first element. It has one proton. Any element, or any atom, I should say, any atom that has one proton is and always is going to be hydrogen. Any atom that has 6 protons in its nucleus is and always will be carbon. The number of protons defines the element. It defines the atom. It cannot, if you change the number of protons, you have changed the atom. Now, also in the nucleus are neutrons. Now, neutrons are described or abbreviated as N superscript 0. They have no charge. They're neutral, and therefore their name. So that's what we have in the nucleus, tightly packed protons and tightly packed neutrons. Now, we still have to deal with, though, with this idea of atomic mass. If you take the total mass of the protons and the neutrons, then you'll get the atomic mass. How much does the atom weigh, right? Mass. How much does it weigh? And carbon has 6 protons, as I've told you. And, oh, by the way, I'm going to tell you it also usually has 6 neutrons. So carbon has basically a mass of 12, because each proton and each neutron gives us a mass of 1. And I'm not going to go into much more than that. We'll just appreciate that carbon roughly has a mass of 12. Now, outside of the nucleus, there is that orbital, that big light blue cloud that was in the diagram. And out here in the orbital is where the electrons are found. And the electrons are always abbreviated E minus because they have a negative charge. Electrons do. They're very, very small, though. And they're so small that they don't contribute to the overall mass of the atom. So they're very, very small, but they're floating out in that cloud. If we were in the football field, the protons and the neutrons would be squeezed into that apple, and the electrons would somehow be out in the seats, right? They'd be out in the seats. They'd be out wandering around somewhere in the stadium. So let's look at just a cartoon of this. On the upper left, I've got a cartoon of a hydrogen atom. Well, what's in the very center? It says there's 1 proton, right? Hydrogen always has only 1 proton. And floating out in the cloud, there's 1 electron. That's hydrogen. Carbon, in its nucleus, it has what? 6 protons. Carbon always has 6 protons. It's non-negotiable. There is oftentimes 6 neutrons also squeezed into that nucleus. That gives it a total mass of about 12. Also, floating around the outside, about 6 electrons. And oxygen, 8 protons. So oxygen is element number 8. It has 8 protons. It usually has 8 neutrons also in there. So what would its mass typically be? About 16, right? 8 and 8. And it also has 8 electrons out in the cloud. What am I telling you, too, about the charges here? Since electrons are negative, right? I'm telling you that electrons are negative. And I'm going to tell you right now that atoms are electrically neutral. If I just handed you a bunch of atoms, they would have no overall charge. They would be neutral. So what does that tell us? It tells us that the atomic number is the what, the blank, as the number of electrons. The atomic number, what was the atomic number? The number of protons, right? So the atomic number is the number of protons, so that must be what to the number of electrons? Yeah, right? So pretty much equal or equivalent to, or the same as, whatever way you want to put that blank in there. Right? So the atomic number is going to be the same as or equal to the number of electrons. Does that make sense? Right? If you look up in these pictures, what do you see? Oxygen has 8 protons and 8 electrons. Overall, the positive and negative charges cancel themselves out. It's neutral. Carbon has 6 protons and 6 electrons. It's overall, those charges cancel each other out, and carbon atoms would be neutral. So what makes one element different from another? What makes gold different from silver? What makes lead different from silver? Well, the difference is the number of protons. Right? The number of protons is always the defining feature. So this is what alchemists have been trying to change for generations, right? Can we change silver into gold? Can we change one element into another? No, not with the way that we've been trying, right? So it's always about the number of protons in the nucleus. Now, what about the neutrons? So we know what the deal is with the protons, right? They are the defining number. What about the neutrons? They're neutral in their charge, but their number can vary. Okay, there's a variable number of neutrons. And when there's a variable number of neutrons, these variations are called isotopes. Now, you may have heard of isotopes. Isotopes are used a lot in medicine, and those isotopes are oftentimes radioactive. Okay, so isotopes. And like I said, they're typically radioactive, which is a fancy way of saying they're unstable. They break down. And when they break down, they give off energy. So anyone going into diagnostics? Okay, so part of the field of diagnostics is using PET scans. Remember I mentioned radioactive glucose is used in PET scans? Or we can have other types of tests where radioactive elements are injected into your body. And they're following that radioactivity through your body. And when you leave, you're still radioactive for a few days, some of these tests. And so you're told not to cuddle your grandkids too hard, right? I mean, you're really supposed to keep distance away because you're emitting radioactivity. And those elements, as they're breaking down, are emitting energy that can be damaging to somebody else or to your own body. So that's the deal with isotopes. Let me give you a picture of this. So there are isotopes of hydrogen on the left. 3 different isotopes of hydrogen. Regular old hydrogen has 1 proton. Right? Always. Hydrogen always has 1 proton. The most common form of hydrogen has no neutrons. There are no neutrons at all. But there's another form of hydrogen where there is a neutron. Okay? Now, when there's a proton and a neutron, the mass was what? 2. And where do we see the word deuce? Right? 2. So deuterium is a form of hydrogen that has a mass of 2. There's another form of hydrogen called tritium. Why is it called tritium? Because it has a mass of 3. And where did it get its extra mass? There are now 2 neutrons. Not just 1, but 2. Remember, the number of protons can't change. If the number of protons changed, you would no longer be hydrogen. So you're always going to have 1 proton in any form of hydrogen. But it's the number of neutrons that's changing from 0 to 1 to 2. Okay. Now, tritium is radioactive. It's used in a lot of research. Over in carbon, you've heard about this one, I'm confident. Most of the carbon you're going to dig up out of your backyard is going to be good old normal carbon-12. Now, carbon is the 6th element. So how many protons must it have? 6. No negotiation. Carbon always has 6. If I'm telling you that it's carbon-12, 12 is the mass, you know then that that carbon has how many neutrons? 6. 6 and 6 giving us carbon-12. That's the common type of carbon, the most common type of carbon. But there's an isotope of carbon called carbon-14. Well, it has to be 6 protons because it's carbon, but in this case there are 8 neutrons. It is radioactive. It does break down. And when you hear about radiolabeling or radioisotopes and determining the age of things, they're using some of this type of technology or some of these facts to determine the age of things. So that's isotopes. So we've dealt with the number of protons, defining the atom. We've talked with neutrons. They vary, and oftentimes those variations, those isotopes, are radioactive. And now we have to deal with electrons. And it's going to turn out that electrons really are the thing we're going to worry about the most in our little introduction to chemistry. Because when atoms combine, when hydrogen and oxygen combine to make water, right, H2O, electrons are involved. Okay? When CO2, when carbons and oxygens come together to make carbon dioxide, it's going to be the electrons that are going to dictate how and if the elements can come together, if the atoms can come together. Okay? Let's figure this out. So every time there is a chemical reaction, I'm going to assure you that electrons are involved and that electrons are either being separated or shared between other atoms. So let's take a look at what this means. In that picture of the atom, there was that red circle with that big blue hazy cloud on the outside. Now that cloud, where the electrons were found, it's not like the electrons can be anywhere. Okay? The electrons have assigned seats. They have assigned sections to the stadium. They cannot wander anywhere in the stadium. So some electrons are more restricted than others as to where in the stadium they can hang out. Okay, that's my analogy to help you figure this out. The electrons are restricted in shells or in layers that go around the nucleus. Some of those shells are closer to the nucleus, and some of those shells are further away in the outer upper seats, if you will, of the nucleus. And it turns out that one of the key ideas to chemistry is that the outer shell, or what's called the outer orbit, there's always a desire for the outer orbit to be full of electrons. Now, these different shells, these different orbits, have a maximum number of electrons that can fit in them. But an atom wants to have its outer shell, whatever its outer shell is, it always wants to have its outer shell complete. I think of that as my daughters and their makeup. My daughters never want to go outside unless their outer shell is complete. Okay, that's just the way I think about it. And if their outer shell is not very complete, they're not very happy. Okay? So maybe you can imagine that yourself. Okay? So with that thinking, let's talk about carbon here for a second. Carbon, element number what? 6. Therefore it's the atomic number is number 6. It's the sixth. It's the sixth atom, right? It's the sixth element. So it has how many protons?
6.
Absolutely. And how many electrons? Because these are typically going to be neutral. 6, right? So we're going to have our good old 6 and 6. So let's take a look at a picture or a cartoon of a carbon atom. So my green is the nucleus. What am I going to find in the nucleus? 6 protons and 6 neutrons. They're inside the nucleus. And then around that nucleus, in shells, there are going to be these orbits or these shells. Now that first red circle represents the first shell. It's the smallest of all of them and has a maximum capacity of 2. It can only hold 2 electrons. Okay, so let's put them there. 1 and 2. There are the 2 electrons. That shell is now full. But how many electrons does carbon have? 6. So we've got to find another shell, another place for the other 4 to go. So here's the second shell. It's outside the first one. And let's put our 4 electrons in there. 1, 2, 3, and 4. I'm going to tell you now the second shell has a maximum capacity of 8. Okay? The first shell can only hold 2. The second shell can hold a maximum of 8. So, thinking about that rule in chemistry, is carbon a happy atom? Is its outer shell full? No, right? Now, what could carbon do to have a complete outer shell? Gain 4 more electrons, in which case its outer shell would now be full with 8. Or carbon could lose 4 electrons, because when there's an empty shell, it's like it's not even there. You just erase it. So if I could take 4 electrons away from carbon, then what would its outer shell be? Just that inside shell with just 2 It's full, it's happy. So this is why carbon is such a beautiful molecule as the building block for our chemistry. We're said to be carbon-based, beings, right? Our metabolism, our biochemistry is based upon carbon. And as we'll be discussing in a few minutes, lipids, proteins, nucleic acids, and carbohydrates, all those macromolecules are all based upon carbon. Okay, so carbon becomes a beautiful tinker toy for making molecules. So there's that inner shell and that outer shell. I think we've got that figured out. So when two atoms combine, when there's a chemical reaction that occurs, there's always going to be a movement of these outer electrons. And these electrons can either be transferred, that is literally moved from one atom to another, or they can be shared amongst themselves. So let me start off with talking about two different types of chemical bonds. There are ionic bonds and there are covalent bonds. So ionic and covalent. I'm going to start off with ionic bonds. In an ionic bond, there's going to be a complete losing or a complete gaining of electrons. Either way. Okay? So there's a complete loss, a complete giving away, or a complete capture of electrons. The example, the molecule we're going to use as our example is sodium chloride, NaCl. Sodium and chloride ions combine, right? These atoms combine in or with an ionic bond. Now, the little mental word picture that I have for ionic bonds, and I'm not really quite sure if this will speak to you, but it does for me. Somewhere back around 10th or 11th grade, I can remember learning about Western civilization, and somewhere in there I learned about ionic columns. Bear with me. And the ionic columns were a type of Greek architecture, some of the Greek columns that were used in their architecture. And then I remind myself, well, the Greeks, historically, they're broke now, but historically, they were warring people who were conquering, right, taking over lands, gathering electrons. It's crazy, but that's where I get my little mental picture. So ionic bonds, I think of the warring Greeks who were grabbing electrons. Now, they could also be giving them away, right, losing or gaining electrons. Okay? So that's my little mental picture for an ionic bond. So let's look at this cartoon of sodium chloride. In the lower right-hand side, here's a lovely little picture of table salt, what it would look like under the microscope. We've all seen table salt. We're not surprised. If I look at the top, this is a picture, a cartoon of what the atoms would look like as they are arranged. Salt, table salt, NaCl, is a matrix, a cube, if you will, of sodium and chlorine atoms. They are tightly arranged in a cubic structure that we call table salt. How does this work? Well, it's the coming together of sodium and the coming together of chlorine. So I'm going to tell you right now, you don't have to memorize these numbers. I'll always give you these numbers, but you're going to hear them so much over the next couple of days that you'll have them. But I'm going to tell you right now that sodium is the 11th atom, or the 11th element, sorry, the 11th element. So how many protons does it have in its nucleus? 11. How many electrons would it have? 11. Let's place those electrons in our head where they would go. So in the first shell around the sodium nucleus, there would be a small shell that could only hold 2. I've given up 2 now. How many are left? 9. Where are they going to go? The next shell holds 8. So I put 8 of them there. How many do I have left? 1. Where does that 1 have to go? Into yet another third shell. Sodium would really like to do what? Get rid of that 1 and deal with only its second filled shell, wouldn't it? Because that's what chemistry tells us, is that atoms want to have a complete outer shell. And they'll lose or gain electrons to get that outer shell filled. Question? Doesn't that take away the neutral? Very good. Absolutely. So when sodium does that, when sodium gives away that electron, sodium is giving away what kind of charge? Negative, which makes the overall atom now positive. So what you're dealing with, when you're giving away electrons or gaining electrons, the chemically neutral or the electrically neutral atom now becomes what's called an ion. Ionic bonds are made with ions. Now an ion is a negatively or a positively charged atom. So when sodium gives away that electron, sodium becomes what we say is Na plus. One charge. You'll see 1 plus sometimes as well. So sodium has a positive 1 charge, which means that it has what? One more proton than it does electrons. So look what happens. We had 11 protons in the beginning, and we had 11 electrons, right? And what did sodium do, as we just described? It lost an electron. As it lost that electron, now it only has 10. And that gives sodium an overall positive charge. What did chlorine do? Chlorine's down here. I'm telling you, chlorine is the 17th element. Therefore, it has 17 protons and 17 electrons. Let's imagine the orbitals now for chlorine. First orbit, 2. Second orbit, 8. That's 10 altogether. How many are left? 7. Now we're going to have 7 in the third shell. What do you think? The third shell is going to... don't tell your chemistry prof. It's a little bit more complicated than this. But I'm going to tell you that for our purposes, that third shell only also holds 8. So what happens now? What would chlorine want to do? Gain 1, so that outer shell is full with 8. And that's exactly what it does. That's what makes sodium and chlorine such a beautiful pair, because one has an electron to give up, and one can take that electron from it. So chlorine starts off with 17 electrons. It gains an electron. Now it has 18 electrons. Chlorine becomes an ion. It now has an overall charge of 1 minus, or Cl minus. So we call that now a chloride ion and a sodium ion. And these two ions now, or all these ions now, come together and they coalesce into this cubic structure that we like the taste of, right? It's really kind of cool because sodium itself is a metal. And chlorine on its own is a gas, kind of poisonous. And together they make great ketchup. So it's really cool that a gas, a poisonous gas, and a metal somehow come together and create something that we have a liking for. Okay? So this is ionic bond. You're forming ions. You're gaining and losing electrons. Covalent bonds, the other type of chemical bond. Now my word picture for this is not quite as complex. If you rearrange the letters within the word covalent, you will find the word love. And if you love one another, you share. So covalent bonds are all about sharing electrons, not taking them, not giving them away, but in somehow sharing them. Now, some people share better than others. Some days my boys share their things well, and sometimes they're not sharing so well. So we'll start off with when things are being shared well. When the electrons are being shared equally. When the electrons are being shared equally, and our example for this is going to be hexane. Now, hexane is a molecule. What's a hexagon? How many sides? 6. Okay, again, we're not becoming organic chemists here, but there's a molecule called hexane, and guess what? It has 6 carbons in it. Okay, just remember this as an example, hexane. Now, hexane is a molecule where all of the electrons are being equally shared one amongst the other. Each of those little lines represents a pair of electrons, 2 electrons being shared. And if we did all the little dots in the orbitals and everything, we would see that every carbon in this molecule has a full outer shell, and every hydrogen also has a full outer shell. And these atoms all combine beautifully into this molecule called hexane. That is going to be one example of a covalent bond. But there are two types of covalent bonds. One is where the electrons are being shared equally. That's what I just showed you. I keep doing this backwards. I'll get this eventually. So with hexane, the electrons are being shared equally. When they are being shared equally, we call it a non-polar covalent bond. Non-polar. Let's try to figure out what that word means to you. Non-polar. When I say polar, you think...
Charged.
Nobody said white bears. Okay, good. So polar, right? Poles of a magnet, north and south pole, differences, right? If you have a lot of polarity with a friend, you have a lot of differences, if you will. And so if there's no polar, non-polar, then there is no difference, and the electrons and the molecules are all working together in a cooperative way. Let's compare that with a polar covalent bond. A polar covalent bond, our example is water. Good old water. And water is an example where the oxygen and the hydrogens, they are sharing their electrons, but they're not sharing their electrons equally. There's some tug of war going on in this molecule, such that we see in the molecule the big red oxygen, and we see the two hydrogens attached. But this little scale over here on the side tells us that the green areas are more positively charged, and the oxygen and the red areas more negatively charged. So within the water molecule, there's some tug of war going on. Yes, the electrons are being shared, but they're not being shared equally. It's like the back seat of my car on a long trip, right? The kids are fighting over something, and they're tugging on it. There's some polarity going on. So they're both covalent bonds, just to clarify. The hexane was a non-polar covalent, and the water is our example of a covalent polar bond, or polar covalent bond. Now, if this is feeling comfortable to you, this whole conversation, maybe you've had some chemistry and you're saying, okay, I got this. I just need to look at it, but I'm okay. Good for you. And when you do your pre-lab for lab number 2 next week, that pre-lab walks you through this conversation. Next week in lab, we're dealing with pH and chemical bonds a little bit, and the pre-lab is going to walk you through ionic and covalent molecules, and it's going to use sodium chloride and water as the examples. So you're going to get a chance to interact with this material in a very good way. If you're really like, whoa, you're talking a foreign language, Mac, I don't really know what's going on right now, then you want to grab chapter 2 of your book, start reading a little bit, and before I do a bit of reading, but I would probably first go to the Amerman lab manual. For those who have it, it's coming in. I'll get that copy to you. But the chapter 2 unit is on chemistry, and it is on chemical bonds. And if you'll read through the Amerman, it's a very succinct, nicely written little introduction. And then you'll do these pre-lab exercises that will walk you through the electron movement of sodium and chlorine and of water. And I think you'll walk out of it much stronger. Okay? So regardless if you're feeling comfortable or not, don't wait on that pre-lab for lab 2. Go ahead and get it done this weekend. I know some of you have lab on Monday, but go ahead and start working on that. That's another reason why I have the first exam way out, because I want to make sure everybody goes through lab 2, interacts with the chemistry before we have this exam. Okay, so that's another reason why it's out a couple weeks. Now there's another kind of bond that I want to introduce to you, and that is hydrogen bonds. This is different from covalent, different from ionic bonds. It is a unique or a special type of bond between hydrogens, right? Hydrogen bonds, between hydrogens and other negatively charged atoms, usually water, or usually oxygen. For the purposes of our example, I'm going to say that it's a weak bond, or really more of a weak attraction, between hydrogens and oxygens, not within the same water molecule. Okay, let me be really clear on this. So if you look at this picture, these solid lines in here represent what? Covalent bonds. And you see that the water has a partially positive charge and a partial negative charge. You see the positive and negative sign. So all of the hydrogens kind of have a positive charge, and all the oxygens have a negative charge. So what hydrogen bonds are is really an attraction between the hydrogens of one molecule to the oxygen of another water molecule. Not within the same molecule, but within neighboring molecules. And you've all experienced hydrogen bonds in one way or the other. This is why when you fill up a cup of water to the very top, and you would think that the water would start spilling over the top, but it actually forms a little dome. The reason it forms that little dome is that the water molecules are actually attracted to one another through these hydrogen bonds and are actually holding on, right, before they spill over the top. This is the reason why small insects can walk on water. There's enough surface tension in the water that insects can walk on it, and this is why it hurts so much when you do a belly flop. Right? So when you land flat on a surface of water, you can stick your finger in the water, no problem. But suddenly when your whole back is hitting it, you're suddenly aware of the collective power of these hundreds of billions of hydrogen bonds that suddenly are kicking back at you and saying, hey, dummy, you should do a better dive next time. Right? So we've all, we experience this. And I forget what the number is, but a person who jumps off a bridge into a river can't survive over, is it 60, 70 feet? Rare to survive. What is it?
3 stories.
30 feet. That all? Okay. Not very far, right? Because, really? How high are those high dives? Anyway, not too far, right? So it doesn't take a whole lot of distance for you to jump into water and to do some major damage or even kill yourself from that collective pressure of all these hydrogen bonds. Okay. So that's our little story about electrons, right? We had to understand the electrons because the electrons are doing what? They're either being transferred or shared. And that's going to dictate how molecules go together. If I give you a bunch of carbon and oxygen and hydrogen, how are they going to rearrange? Depends on what the electrons tell you. Right? The electrons are going to dictate how and when and if molecules are going to combine to make molecules. So there we are, right? We were just talking about atoms. Now we're making molecules, aren't we? Sodium chloride, water, CO2. So a molecule is when you take one or more atoms and put them together in a chemical bond. Water, H2O. We know that it's even more specifically a polar covalent bond. Or we can have a compound, which is when you take different types of atoms and put them together. And one example would be C6H12O6, and you may know that or recognize that as glucose. That's a simple sugar, glucose, C6H12O6. What does that tell us? That glucose has what in it? What does this tell us? Glucose has 6 carbons attached along with 12 hydrogens and 6 oxygens. And all of those atoms are working together to create a unique molecule called glucose. Questions? How are we doing on chemical bonds? Protons, neutrons, electrons. That seem reasonable right now? I'm going to go for a couple more minutes, then we'll take a quick break. Okay, give me a couple more minutes. So, dissociation. How do these molecules go together? When you eat a meal, you take food into your body, and what does your body do with it? Breaks it down into smaller pieces, and then what does it do with those smaller pieces? Absorbs them, but then your body has to make your bones. The body has to make your muscles. The body has to make your structures of your body. So your body's going to take in molecules of energy. It's going to break them down into their individual pieces, and then it's going to resynthesize and make the things that the body does need. So let's talk about how this works. So dissociation. If I say to you dissociation, what comes to mind? Anything? Dissociation in this sense, what I want you to think about is that when I take a molecule and I put it into water, especially like sodium chloride. If I take sodium chloride and I put it into water, what happens? We know what happens. It, quote, dissolves. The word, though, I want you to use instead is that it dissociates. And what that means is that when I put sodium chloride, salt, into a beaker of water, those salt crystals are going to break apart. They're going to dissociate. They're going to, quote, dissolve. Let's figure out what's going on here and why is it that salt dissociates when I put it into a beaker of water. Remember, water is what? My little Mickey Mouse ears down here. Water is polar, right? Water is polar. That means that it's partially negative and partially positive. And that's what's important as we consider what happens when I take this salt crystal. That's a huge old crystal, right? But if I take this salt crystal and I put it into water, what's actually happening? The crystal is going to dissociate. And that means that the sodiums and the chlorines are going to be pulled away from their cube and they're going to interact with water molecules. But look how the water molecules are going to interact with it. Here's a sodium right in the center of this cluster. And what is it that's facing the sodium? Water, but in what orientation? Which way is Mickey's turned? Mickey's got his what? His little, you see the Mickey ears? So Mickey's doing what? Sodium is positively charged. What part of Mickey is leaning up against the sodium? The red head, right? Look at chlorine. Chlorine, though, it's negatively charged. And now the water molecules are going to crowd around the chlorine, but how's Mickey going to be? With his ears. Right? Because the ears are positively charged. Okay? So this is what's going on. The molecules actually being dissociated, pulled apart, and surrounded by water molecules. Now you keep pouring salt into the beaker, and what happens? It just keeps on dissociating, dissolving. There comes a point, though, where you add more salt and it doesn't really dissolve anymore, does it? What can you do to make it dissolve even more or to dissociate even more? Stir it, add more water. That's cheating. Right? But what could you do? I heard heat and I heard stir. What do you do when you're stirring it? Imagine you're a little magic school bus and you're down in this molecular, reaction. What's going on as you stir it? You're creating what? New opportunities for water to interact with chlorine and sodium. You're creating new arrangements. So more salt will dissociate. After you stir it, you could then heat it. And by heating, what are you doing? Heat is actually causing the molecules, once again, to kind of bounce around and dance. And that's going to also force more water and ions to interact. At some point, though, stirring and heat, you're still going to maximize, absolutely maximize the ability of the salt to, quote, dissolve in the water. Yeah, you could add more water, right? You're creating more opportunities for dissociation, right? So that's what's going on. Can you picture that? Now, that's not only just for table salt. That's for everything. Everything that's floating through your blood, everything that's floating through your body is surrounded by water molecules. And it's that surrounding of water molecules that allows the molecules to be carried through your blood. Let's take just a couple minutes break right here. Let's say about 5 or 6 minutes. I'll let you stretch, regather your thoughts, and then we'll continue on. Okay, so before I go on, I just want to mention a couple of things about the My Readiness test and the Mastering A&P. The Mastering A&P, that's what comes with the textbook. There's that red card with the code. I'd really like everyone to get registered for that as soon as possible so that you can go in and do the homework assignments and just kind of get oriented to all of that. How many of you have already done the Mastering A&P registration? Okay, so most of you, great, thank you. Now, in addition to that, a different ticket, a different item is the My Readiness test. Now, the My Readiness test was meant to be a pre-test. You go in, you do it once. It's timed, it's 60 minutes, it's 70 questions, and it basically has a smattering of questions about study skills and basic things in anatomy and physiology and cell biology. Your score on that is simply meant to be a diagnostic indicator of where your areas of strengths and your areas of weaknesses are. You only do that quiz once. After you do it, it will then allow you to do some tutorial helps to help you in your areas of greater need. Your score on that, regardless of what score you get on it, I'm going to give you all 10 points for doing it. But I didn't want to make that common knowledge because I was worried that students would, oh, he's going to give me full credit. I'll just click A all the way down. I don't care. I'm out of here. I wanted you to try to your best ability and then have it be a true indicator of your areas of strength and your area of weaknesses. Now, you can go back into My Readiness, and there will be some tutorials, basically some extra help things that will help you gain knowledge. Maybe you're not very good in math and it picked up on that. Or maybe the genetics section, or maybe the cell biology section, or maybe the study skills section. There's like 6 little subsets within the whole test. So that's what that was all about. I would like you to do that My Readiness test no later than next Monday, within 1 week of the class, because I really want it to be a pre-test before we get into any significant knowledge here. Okay? Now, there's also an assignment that I'd like to have done by Friday when you go into My Readiness. When you go into Mastering, right, the whole big suite. There's an assignment that I have due on Friday, and that is simply a, can you figure out how to use Mastering? It's just walking through, this is what you need to do for Mastering. There's one more thing I want to point out. When you go to masteringamp.com, and you go to sign in your name after you have registered, or even as you're registering, right below your name, it says something like, check my computer. Check my computer, check my system, something like that. Click on that. It will give you in 10 seconds or less a breakdown of how well your computer is equipped to do everything within Mastering. And if you don't have an updated Firefox or an updated Chrome, or maybe your Flash player or your Java is out of date, it will tell you that, and it will tell you how to update those plugins. Those plugins, if they're out of date, you may not get Mastering to work well. And you can always troubleshoot. So you don't need to be wondering, am I having trouble because my computer's not up to date? It will help you get up to date. Okay? So definitely also take advantage of that check my computer. I think that's what it says. It's right below the sign in, and you can check that often. Every once in a while, just click on it, and it will tell you if there's been some update to Java or Flash that you should also consider updating. Is that clarifying the whole My Readiness and the Mastering AMP? Yes, ma'am.
The calendar that first comes up, everything that's highlighted, those are all the assignments. There's no other place to look.
Everything is in one place. There's only 4 things on there right now. There's an assignment due on Friday, that introduction. There are 2 homework assignments not due until the 28th, which is the day of the exam. So the homework assignments, it's not like you have to wait till the 28th to do them. That's the last that they're due, and they're due before you take the exam. The idea is to do them, and you can do them multiple times until you have mastered that content, but you have to have them done before the exam starts on that Wednesday. Now, on the Monday, the 26th, that's the holiday, isn't it? Mm-hmm. But at midnight, I think it's midnight that night, I have the first quiz due. Now, it's due 2 days before the exam, so that you get the quiz done. Now, can you do it sooner? Absolutely, right? But I wouldn't suggest putting it in tonight. But I mean, wait till next week, and then you can start looking at the quiz. And you want to submit it no later than Sunday night at midnight. And then on Monday morning at 12:01, it'll become available for you to review. So you can look over it. I said the wrong day. Tuesday morning, it'll become available. And you can look over it, see where your areas of strength and weaknesses are, and then fix those areas before the exam. So there's only 4 things. That's what you're going to see when you get on there. Okay? Is that consistent with what you're seeing? 4 assignments, 4 things right now on the Mastering calendar. Any other questions about Mastering? Yes?
So the assignments are the ones that you have to get like
80. Shoot for at least an 80. You could get it done the first time, or you could do it the 15th time. I don't care. But at least once get 80%, it will capture the highest grade.
So there's no like other assignments hiding in Blackboard somewhere or anything. Just one spot. Right?
Everything's going to be in mastering at this point. Now, I will be sending out any kind of emails. I'll be reminding you in class. Anything that's going to come up, I'll be reminding you. You'll be sick of my reminding you of it.
When we go to redo them, if you get lower than an 80%.
Keeps the highest.
Right. But do we, does the program allow you to only do the ones that you missed, or do you have to redo the whole
You know, right now, the question was when you are redoing the homework assignments, do you start over from scratch, or do you just build upon what you already had? I do not recall.
Okay, so you don't know if it tells us which ones are wrong.
I know that in old days, in a previous publisher, I had a choice over that, and I don't recall right now which way this one's going to go. People would complain either way. People would want to have the whole second time to practice it, and then there'd be people like, I already know that. I already got that right. I just want to work on the things I didn't know. No matter what I did, I always had people complaining. So I don't recall which way I have this one set. If you don't like it, let me know, and then somebody else can complain about it next time. There are two different ways of thinking about it, right? Repetition, doing the whole thing twice, 3 times is good, or, hey man, I already know that. Why do I have to spend my time doing it again just to get a higher grade? I don't know. Good question. Keep me posted as what you discover, and let me know if you like it or not. Anything else about online stuff?
When you get the wrong answer, does it tell you what the right one is?
I think it
No,
does.
you get 5 attempts.
Yeah.
Oh, yeah.
Yeah. I mean, if it's A or B, shouldn't take you 5 times to figure that one out, right? True, false, or or labeling things. Yeah. So I think you'll find it to be very intuitive and very helpful.
It's
Yeah.
not they're very helpful. I think.
It's
difficult, but
what's it called? Mastering, right? It really is a helps tool. So I hope you'll enjoy it. It is, like I said to you last time, maybe not in very much detail, this is a new book. We are one of the first colleges in the country to use the second edition. They just rolled it out. That's why your book was so late getting to the bookstore. They just got it published. This is published as 2015. Crazy, right? So they've already, this thing is as new as it can be. And actually today I'm expecting a shipment from Pearson. That's going to be one more thing that I'll be handing you as a part of this package. It did not get to me yet. You've already paid for it. I'll be getting it to you. It didn't give it to me today, so I'll get it to you on Monday, I'm confident. Okay, so more things for you to study from. Okay, so let's keep going then with our conversation here about chemical reactions. I hope I've convinced you that when carbon and hydrogen and nitrogen or other molecules combine, or atoms combine, it involves electrons. So let's figure out some different combinations here. Chemical reactions. One would be considered a synthesis reaction. I mean, the name kind of tells you what's going on. You're synthesizing something. You're making something. You're combining atoms to make something else. The basic equation for this would be A plus B goes to or creates AB. When you see the arrow in chemistry, that means creates or makes. And every time you see an arrow, you know that there's a chemical reaction. And every time there's a chemical reaction, there is a movement or a rearrangement of electrons to make that occur. So we have synthesis reactions, where we take 2 smaller molecules and combine them into something larger. Now, another way of saying this is that this would be an anabolic reaction, or this reaction would be part of your anabolism. We're all familiar with the word anabolic steroids, right? Anabolic steroids are things that people take to do what? Build up muscle, right? Build up. So anabolic means to build up, or to create, or to synthesize. These are all sort of synonymous words. So synthesis reactions, you can think of it as also being an anabolism or anabolic, because you are synthesizing or creating something. And typically, when your body is putting things together, it's going to take energy. Just like if you're building a house, you're going to have to swing the hammer. You're going to have to put energy into the situation to make it happen. So what you're going to find is that anabolic reactions, more often than not, require energy. Now, in biology, that energy is in the form of what? ATP. Okay, so ATP, we'll talk about ATP quite a bit. But ATP is the molecule that your cells are making in order to facilitate or to give energy to these reactions. So if there are synthesis reactions, there must also be decomposition reactions or breakdown reactions. And the basic way of writing this would be that AB is broken down to its individual components, A plus B. Now, when this happens, typically there is energy released. There is the release of energy. This is like when a building is imploded, right? When something breaks down, when they implode a building, there's all that sound and all that energy that comes crashing down to the earth. So when things are broken apart, there's usually energy released. When you eat a Snickers bar and your body is taking in those, we'll call it nutrients, right? That sugar and all those nutrients, your body's breaking down those molecules. And as it breaks down those molecules, you are gaining energy. Right? So as we break down energy, now the overall term for breaking down reactions are catabolic reactions. So anabolic, we're building up. Catabolic are breaking down. Then there are some other reactions in your body. We won't give any specific examples, but some reactions can go either way. So you'll see the double arrow here, going to the left and going to the right. We'll deal with those situations next semester. So in this cartoon, I know it's small, but I want to show you what you've got here and appreciate what you have. At the very top, each of those green hexagons represents a sugar molecule. This is a monosaccharide. One sugar, monosaccharide. And all I'm showing you here is that one monosaccharide can be chemically connected to another monosaccharide to form a disaccharide. Now, when two monosaccharides are chemically combined to make a disaccharide, that means that a chemical bond is being formed. Now, when a chemical bond is formed, you know the electrons are being rearranged. Now, when molecules like this are put together, it usually requires what? Energy, right? Energy is involved. So we can take two single sugar molecules and we can combine them to make a disaccharide. But notice there's also a reverse arrow up there. So I can also go the other way. I can take a disaccharide and I can break it down into its individual components. That's all I want you to see on this particular picture. The top is what goes on with carbohydrates. The bottom is what goes on with the making of proteins. And the middle is what's going on with the making of lipids. It's pretty much the same story over and over and over, that within your body, your molecules, your biochemistry is repeating the same idea over and over and over. We'll come back to this as it makes more sense. Now, I mentioned to you that the energy, or that these reactions require energy, or that they need extra help. Now, from a chemical or a physical standpoint, energy is defined as the capacity to do work. Right? So I need energy to get some kind of work done. I need energy to combine molecules together. There's a couple different types of energy that I want you thinking about. The first one is potential energy. To me, the word picture I have for potential energy is a 5-pound bag of sugar in my pantry. That 5-pound bag of sugar has the potential of being used when making cookies, to be ingested by my kids to create energy, right? It's just sitting there waiting to be used. It has the potential. Another analogy you'll hear is about a rock sitting at the top of a cliff or at the top of a hill. And it's sitting there, just waiting. Now, if that rock gets pushed a little bit, then it will start tumbling down, and now energy is being released as it comes tumbling down. Okay, it has the potential of releasing energy. But it's not doing so at the time, right? It has it has stored energy. So that glucose, that sugar that I have in my pantry has the potential to release its stored energy. Another type of energy is kinetic energy. Now, anybody heard of kinesiology? Right? Kinesiology is the study of movement, right? So kinetic energy is the energy associated with movement. When you heat something up and the molecules are moving more and more, as we were talking about how to get more sodium chloride to dissociate in water, as you heat up the beaker, there's kinetic energy going on because the molecules are now moving more. And then the third type of energy that I want you to know about is activation energy. What does it sound like? The energy needed to start something, to activate something. And this is what's going to be necessary in the body to jumpstart many of your chemical reactions. I said there could be a boulder sitting at the top of the hill. It could be sitting there for decades, centuries. Someone, in order for that boulder to start moving, would have to come along and do what? Hit it or shake it or whatever, right? To activate it. So activation energy is the energy necessary to jumpstart a reaction, in this case a chemical reaction. Okay, I think I stopped. I don't know how far back it was, but we'll pick up here. So an enzyme is going to lower the activation energy. So what does that mean? It's going to lower the amount of energy needed to start the chemical reaction. Okay? It's going to lower or minimize the amount of energy needed to get that thing started. So let me give you a picture of this and how enzymes work. This is a cartoon representation of a reaction. And over here on the left-hand side, you've got this ball being pushed up this ramp. And then once that ball gets to the top of the ramp, what's it going to do? It's going to glide down to the bottom with no problem. Now, in order for this ball to get to the top and to glide down, it has to be pushed up, right? So that pushing up, whatever energy is necessary to push up that ball, would be the activation energy. Okay, that's the activation energy, the amount of energy that's needed to get that ball to the top so that it can spontaneously come down to the end. And this is what enzymes do in a strange kind of way as far as this picture. This is the same graph, except now we're not dealing with a ball being pushed up. Now we're dealing with the chemical reaction. So we have over here the reactants. Let's say it's A and B. And the reactants are sitting over there, and how big the hump is represents how much energy would have to be put in to activate the chemical reaction. So what I see here is that the blue hump would take a lot more energy to push it up and get it going, and the red hump is lower. This is what an enzyme does. The enzyme says, well, typically you would need as much energy as the blue hump to make it go, but the enzyme is going to lower that amount of energy and allow it to happen more easily. And it's marked here as E sub A, energy of activation. Right? You'll hear activation energy or energy of activation. And so what happens is that the reactants start in the chemical reaction. They get to the top and they finish at exactly the same place. This is the products. Nothing has changed. The reactants are the same. The products are the same. What happened? The whole thing was allowed to occur much more easily. Okay, so that's a picture of what enzymes do when catalyzing a reaction.
Is the speed the same?
The speed actually is faster. Enzymes also speed up reactions. And they do that. I mean, you could have, for two molecules that need to have an enzyme to come together, you could have those molecules together for a year and nothing would happen. You put the enzyme there, suddenly they go together. So it not only makes it easier, but it absolutely does speed it up. Right? It makes it more likely to happen. Now, the cool thing about enzymes is that they're reusable. So enzymes, when they're in your body, are being reused. And some enzymes do their job 10,000 times a second. We're not talking about some slow process. So enzymes can do their little magic trick 10,000 times a second and be reused over and over and over and over. So they're a very remarkable protein in our body. Our biochemistry would not occur without it.